Well, good day, y'all, and let us continue on our mission to understand thermochemistry. And let us take a look at this. Consider this reaction. I have my calcium ion, and it's reacting with hydrogen carbonate to form calcium carbonate. And this occurs at constant pressure. And during this reaction, some heat is absorbed, 38.95. Now, what's kind of interesting is this reaction also forms some CO2, and in doing so, 2.47 kilojoules of PV work is done on the atmosphere. And we want to know the values of Q, W, and delta H. Okay, well, I think there's some terms that we need to learn a little bit more about, such as work. So let us go back, and we are doing Thermochem, right? And we've learned some things about Thermochem. We said that, thermochemistry does what? It focuses on chem reactions and energy changes, and maybe the associated energy changes involving heat, right? And I said, hey, really, what this is all about is heat. Maybe I should say chemical reactions and heat. That's what we're really focusing on in Thermochem. And I said we already know something about heat, right? We learned that in a previous unit. Heat is little q, and we said that heat is equal to what? It is the transfer of energy between objects of different temps. Good. Now, there's another term in here that we started talking about. We talked about energy, right? And we said, what is energy? Energy is the capacity or the capacity to do work or produce heat. Okay, we understand what heat is, but what is work? So let's come out of our discussion of energy and talk a little bit about work. Good. So what is work? Something we try to avoid. No. Work is really a force applied through a distance. That's at least what my physics brothers and sisters would say, right? Force applied through a distance. Now, so F is equal to, work is equal to F times D. W is what we use for work, W. And so W is equal to F times D. Now, there's a special case for chem. The special case for chem is what we call PV work. PV work. And what we usually mean here is I have a cylinder. Let's say I have something like this, and I have a cylinder like a piston. Yeah, piston would be cool. And I have a gas in here, and it combusts. And when it combusts, let's say that is something like octane in here. So when my octane combusts, what happens? It pushes my cylinder and it changes the volume. And so the change in pressure volume, and usually we look at pressure being constant, so we'd say the pressure times the change in volume is a form of work. And so this is an important chemistry definition of work. And because the work is done on the system, we'd say that work is equal to negative P delta V. Okay, so that's kind of a chemistry definition of work. This is a physics definition of work. And so we know a little bit about work. And we said the other thing here, when we talk about what is energy, heat, Q. And now the one question is, let's talk about the signs, the convention. Well, we know something about Q when my reaction produces or produces heat. we say that is exothermic, and my Q is negative, right? When my reaction absorbs heat, we say that that is endothermic, and my Q is positive, right? And really what we're saying here is what? As we mentioned last time, that my reaction is my system, right? System. So it's, maybe I should draw this better down here, right? We have lots of space. So my reaction is my system, right? That's my system. So if heat leaves my reaction, it goes from my system to the surroundings. We say that that is Q equals a negative. If the surroundings add heat to my reaction, then we say we look from the perspective of the reaction. Heat is coming in, so Q is positive. Well, what about the conventions for work? When work is done by the system, then I say that this is work is less than zero. It's negative work. And when work is done on the system, then that is positive work. Got it? W is, so if my reaction is doing the work, if it is doing the work, then we say that is a negative value. If my surroundings are doing the work on my system, then that is positive. Got it? Okay, good, good, good. And we have one other thing I think we want to talk about here, and I guess I'm going to bring it off of this. We're going to get into something which we are a little bit familiar with, but we want to talk about delta H. What is delta H? Delta H is my change in enthalpy, right? And here's the cool thing. Here's what we really need to know is at constant pressure, and in AP Chem we'll show you how this is derived. At constant pressure, delta H is equal to Q. So as long as I'm at constant pressure, my delta H is equal to the heat transferred. And that is an important thing for us to remember. Good. And then the signs of my delta H will be the same as the signs of my Q. So when I have an exothermic reaction and Q is negative, then my delta H for that reaction is negative. When I have an endothermal reaction, my Q is positive, means my delta H is positive. Got it? All right, I think we can answer the question. Here we go. During the reaction, I have 338.95 kilojoules of heat is absorbed. So here's my reaction. It absorbs 38.95 kilojoules, right? And it says, and in doing so, it does 2.47 kilojoules of work. Okay, so what's my Q? My Q is, hey, the heat is going into my system, so it's a positive 38.95 kilojoules. Work is being done by my system, so that means it's going to be a negative value. And what is that value? Negative 2.47 kilojoules. And what is my delta H of reaction? Assuming that this is constant pressure, then delta H is equal to Q at constant pressure. So the delta H for my reaction would be the same as my heat transferred. Zoink! Yahoo! Cool. Got it? I think I can do this. Let's see if you can do it. All right, I'll give you a few seconds. Come back when you're ready. Since it absorbs 140 joules and does 85, let's make sure I read that last one right. Work on the end. Doing so, and in doing so, do. How about does? The reaction also forms, and in doing so, does. Okay, good. I did read that last one right. Here we go. It absorbs 140 joules from my surroundings and does 85 joules work. So here's my system. The reaction occurs. It sucks up 140 joules from the surroundings, and what does 80, and it does 85 joules work on the surroundings. Good. So that means my Q is equal to a positive 140 joules. My W, since it's being done by the system on the surroundings, is a negative 85 joules. And my delta H is going to be the same as my Q, which is 140 joules. And we're going to assume it's at constant pressure. Piece of cake. Let us move on. Ay, caramba. What is this? Well, it looks like I have a reaction. I have a delta H. What is delta H? Okay, we're learning some stuff about delta H. So let's go back to our notes and add some more on delta H. Good. So we're talking about delta H here. It's the change in enthalpy. And let's change colors. Now, delta H, we said, is equal to Q at constant pressure, but what else? This thing is a extensive property. You guys remember what extensive properties are? That means amount matters. So if I have a reaction, let's say I have X plus 2Y goes to Z, and my delta H there is equal to 142 kilojoules. Well, that means that 142 kilojoules means for 1 mole of X and 2 moles of Y and 1 mole of Z. If I double this, 2X plus 4Y yields 2Z. That means I have to take this number and multiply it by 2. So the delta H for this reaction is 2 times 284. Kilojoules, 2 times the one above, right? Cool. The other thing that's kind of cool is direction matters. Direction matters. Direction of reaction matters. So back to our X plus 2Y yields Z. Let's say my delta H for that is 142 kilojoules. Well, then what is Z going to X plus 2Y? Well, that's the reverse of the first reaction, which would mean my delta H is the same magnitude, but different sign. So this reaction is what? Endothermic. The reverse then has to be what? Exothermic, and the same amount of energy is transferred in both cases, just going in different directions. Got it? Okay, let's see if that helps us here. So I have 2 hydrogen gases reacting with oxygen going to 2 waters. What is the delta H for? Okay, I have 4, 2, 4. So what have I done? I've taken these coefficients and I've done what? Multiplied them by 2, correct? Zoink. And zoink. If I multiplied those by 2, how do I get my delta H? I have to do what? Take that and multiply it by 2. So 2 times 483.6. I think I can do this in my head. 2 times 6 is 12. Yoink, carry the 1. 6, 7. 16, carry the 1. 8, 9. There we go. Negative 967.2 kilojoules. So if I have 2 moles of hydrogen reacting, I produce, man, I can't even see what I produce. Zoink, 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 doink, magic. I love it. If I have 2 moles of hydrogen which react, I produce negative 400, I produce 483.6 kilojoules of heat, right? So if I double that amount and I have 4 moles of hydrogen reacting, I will double the amount of heat. That makes complete sense. Okay, now what happens here? what have I done? Well, I've gone from the forward to, now I have reversed my reaction. So if I have 2 moles of water that are decomposing instead of 2 moles forming, then I'm going to what? Not create, but absorb 483.6 kilojoules. Got it? Hey, wonderful. Yahoo! Now let's see what you can do. Bring me back when you're ready. Okay, so what have we done here? Well, it looks to me we had 1, 2, 2, 1. Water's on this side. Now when I look here, I have water on this side. So the first thing I did is what? I reversed it, so we reversed our reaction. So now we're looking at delta H equaling not a negative, but a positive 890 kilojoules. But not only that, what? I had a 2 in front of here, and now I have a 1 in front of here. So what did I do to all my coefficients? Oops. What did I do to all my coefficients? Yoink, yoink, yoink. I divided by 2. So if I have all of these divided by 2, then what has to happen to my delta H? It also has to be divided by 2. So delta H for this reaction would be 445 positive kilojoules. How many of you got that right? Wunderbar. How are we doing on time? Not bad. Let's see if we can go on. Are you ready? What's the next one? Okay. Great. We can handle this, right? I have 2 hydrogens, 2 moles of hydrogen reacting with 1 mole of oxygen, forming 2 moles of water, gas. And the delta H for that is a negative, the heat of reaction we'd call that, is the negative 83.6 kilojoules. How much heat is released when 3.5 grams of steam are produced? Okay, here's what you have to understand, is this number really means to negative 483.6 kilojoules per what? Per 2 moles of hydrogen, or it is a negative 483.6 kilojoules per what? 1 mole of oxygen, or it's a negative 283.6 kilojoules per what? 2 moles of water. That's what you have to understand, right? But do we have 2 moles of water? No, we have 3.5 grams of steam. Oops, yes, steam. It is gaseous. So what do we have to do? We're going to take our grams of steam and make moles of steam. Moles. So we're going to take, how do we get moles? We're experts at this. 3.50 grams times 1 mole of H2O per 2 times 1.008 plus 16.00. And what do I get? Let's get out my handy dandy HP 30XA, and I take 3.5 divided by quantity 2 times 1.008 plus 16, and I get 0.1942. How many sig figs? I have 3, so I want to carry at least 1 more. Moles of H2O. Now what do I do? Well, what do I know? I have 0.1942 moles of steam times what? A negative 483.6 kilojoules per what? 2 moles of steam, right? And we do our dimensional analysis, and what do I get? Times 483.6 divided by 2, and then my answer is 46.97, which is equal to 47.0. And what's the sign? Negative, negative kilojoules. So how much heat is released? How much heat is released when 3.5 grams of steam are produced? The answer is negative 47.00 kilojoules. Good. You guys do this one. Bring me back when you're ready. All right. What do I know? Well, I have a negative 890 kilojoules per 1 mole of methane per 2 moles of oxygen per 2 moles of water per 1 mole of carbon dioxide. How much heat is released when 125 grams of methane? So what do I want to do? I want to get the moles of my methane, which is equal to 125 grams of methane times 1 mole per 12.01 plus 4 times 1.008 grams. And what do I get there? So I take 4 times 1.008 plus 12.01 equals, what's 12.01 plus 4 times 1.008 equals 16.042. Invert times 125, and I get 7.792 moles of methane. Good. And what's my relationship? It is a negative 890 kilojoules per what? Per 1 mole of methane. Wow, this is just like what? Yeah, it's just like stoichiometry, right? And mole ratios times 7.792 moles of methane. My moles of methane cancel, and what do I get? Times 890 negative, and it looks to me like I get 6935 kilojoules. What's my sign? Negative. Yoink. So that would mean 6,935 kilojoules are released. Cool. How much heat is released when 125 grams of water are produced? Okay, same thing. Moles of H2O equals 125 grams of H2O times 1 mole per 2 times 1.008 plus 16.00. And what do I get? 2 times 1.008 plus 16, invert that, times 125, and it looks to me like I get 6.938 moles of H2O. What's my relationship here? It's a negative 890 kilojoules per what? Zinc, 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 per 2 moles of water formed, per 2 moles of H2O. But how many moles of H2O do we really have? 6.938 moles of H2O. My moles of H2O cancel, and what's my answer? So 6.9 times 890 negative divided by 2, and my answer is a negative 3. Oh, how many sig figs do I get out of here? 3. 2. I only get 2 sig figs. Hey, that should only be 2 sig figs. Negative 6900 kilojoules. Sorry, 2 sig figs. Only 2 sig figs down here. Zoink. So it'd be there. So when I round that to my proper number of sig figs, it's a negative 3100 kilojoules are released. Great. Wonderful. All right, I'll tell you what, let us stop right here for today. I think that will be plenty. Next time, we're going to get into something called Hess's Law, and that has more to do with my delta H, my change in enthalpy. Have a good day, y'all.